Thank you for your introduction. My name is Yuji Suzuki from the University of Tokyo, and actually this work is done by my student Seonwoo Kim. And I think I don't have to explain, but our target is to develop MEMS-based electric generator for vibration energy harvesting. And as you might know, Electret is a dielectric with quasi-permanent charge. So charges stay there for tens of years and generate electrostatic field externally. And the advantage of electric energy harvester is that we can get higher power output or higher output voltage at low frequency vibration and in small scale. And this is a schematic or principle of vibration energy harvesting. And when this top plate with electrode is vibrating in the horizontal direction, you can generate induced charge on the bottom electrodes. And by changing the amount of induced charge on the bottom electrodes, you can induce AC current in the external circuit. So my group is spent like 15 years for this electric generator, and we made several prototypes of electric generator. And actually, for electric generator, package is necessary to avoid humidity or dust because of those, especially humidity induce charge decay. But usually we use thermal bonding or seam welding for reliable packaging. But the thermal cycle during those packaging process will induce charge decay if the device is already charged. So the purpose of this research is to propose a post-packaging charging method using soft X-ray radiation and to develop a model for estimating charging time for soft X-ray charging after packaging. So for this, by using this soft X-ray charging, we can use it, as I said, the reliable packaging process using thermal bonding also. So today's focus is the charging process, new charging process. So we usually use corona charging, but we have some mainly two limitations. Firstly, we have to use a charge and assembly approach. So first we expose electric film and charge with corona ions and assemble the device or package. Or to charge, it is very difficult to charge three-dimensional structure because of the charge accumulation at the opening, especially for the vertical electrode in comb drives. So that is why we already proposed soft electrode charging. In this case, we can generate ions in the air gap through in situ photoionization. And so we can separate these charges with bias voltage and attract only electrons onto the electrode to get the negative surface potential. And it is very easy to control surface potential and easy to get the uniform surface charge or surface voltage. So, in this talk, I focus on the post-package soft X-ray charging of vertical electrode on comb drive. So this is schematic. So after packaging, we irradiate soft X-ray, and soft X-ray will penetrate the lead and introduced into the micron gap between comb drive and generate ions in between these comb drives, and we can charge the vertical sidewall using bias voltage. So first we need to develop a model how long time we need to get the fully charged electret on the sidewall. So this is just simple model for charging time. So we assume that charging time is inversely proportional to the number of ions generated or ion current, and also inversely proportional to the ion collection efficiency. We use a soft X-ray source in which the peak energy is 6 keV, and bias voltage we choose is 100 volt. So, the amount of charge can be expressed by integration of products of energy spectrum, lit penetration rate, number of ions generated per photon, and also ionization rate. So this is energy spectra of our soft X-ray source. The horizontal axis is photon energy, and this is penetration rate. And ionization rate from the literature in our COM drive can be calculated like this, right? Again, this horizontal axis is the photon energy. So by integrating these products, then we can estimate number of charges generated. And after generating charges, we have to correct those charges onto the sidewall. Then we use a so-called ionization chamber model. I don't go in detail here, but this is a bias voltage, and this is ion current, and this is charging without lead. So just how to say, normal case. Then the ion current is large, and we need a relatively high bias voltage to capture all the charges. But with 0.1 millimeter thick aluminum lead, then the ion current is of course much reduced, and we need how to say, the collection efficiency is actually high, even with a low bias voltage. So this is a comparison. So without lead, ionization rate is 100%, and collection efficiency is 95%. So charging time is only 2 minutes. And when we consider 0.1 millimeter aluminum lead, then ionization rate is reduced to 3.8%. So that with our soft X-ray source, then we need a charging time for like 55 minutes. So this is a process. So it's very easy, but we use a SOI wafer with very thick box layer, 10 micron thick box layer, and 17 micron thick device layer, and pattern COM drives and spring using deep alloy, and remove box layer using vapor HF. And then after dicing, we bond device onto the package, wire bonding, and then deposit purines 1 micron thick purine C onto whole device as an Electret layer. Then after that, we bond lead 0.1 millimeter thick aluminum lead. Then finally, we irradiate soft X-ray for charging. So this is an actual photograph, and in this device, we have about 450 electrode pairs, and this is a gap closing type electrodes, and maximum amplitude is 47 micron, and Q factor is about 60, and this is a ceramic package and aluminum lid. So after charging, we actually measure the surface potential using Kelvin force microscopy to confirm that we can get the uniform charge. So after charging, we intentionally break the device and measure these points using Kelvin force microscopy. Scanning area is 1 micron by 1 micron, and get the mean surface potential in this case. So So this is, in this case, this is horizontal axis is a vertical depth direction, and this is a longitudinal direction along the finger. And as you can see, we can get the uniform potential 50 volt, plus minus 50 volt, which corresponds to 100 volt bias voltage. And as you see, our measurement data in good accordance with the model. So as you see, we can, after by using 55 minutes charging, we can get almost 100% charging. So this is just a simple power generation test using a magnetic shaker. This is a device packaging with aluminum lid, and so external load is 2 mega ohm, and this is a frequency versus power output for 2G acceleration. This is a this is sweeping up, this is a sweeping down, so we can get the 2 microwatt at the 600 hertz, which corresponds to 30% of VDRG, velocity damped resonance generator limit. Okay, so to conclude, we developed a package comb drive Electret MEMS vibration energy harvester, and we confirmed that the uniform surface potential can be achieved using post-package soft X-ray charging, and charging time is well predicted with current linear model, and we get the 2 microwatt, the 2G, and 600 hertz in our prototype. Thank you for your attention.